Kubernetes makes privileged access a cluster-wide security concern. In this section, we'll connect identities, RBAC service accounts, secrets, and admin controls to practical PAM practices. Least privilege, just-in-time access, auditing, and stronger secrets protection. Up to this point, we've moved from IAM and PAM fundamentals into platform controls. Microsoft Entra PIM, vendor architectures, and privileged access across Linux, Windows, Active Directory, and cloud. Now we apply that foundation to Kubernetes, where identities, workloads, APIs, secrets, and RBAC all shape privilege risk. After that, we'll connect these ideas to vaulting and the capstone. In Kubernetes, privileged access is not limited to an administrator logging in. The API server can control workloads, secrets, identities, and even cloud resources. That means one over-permissioned user, pipeline, controller, or pod can turn a small compromise into a cluster-wide incident. Kubernetes identity starts with an important split. Human identities usually come from outside the cluster, while workload identities are created inside it. A person may authenticate through certificates, OIDC, Cloud IAM, or an enterprise identity provider. Groups make authorization manageable by letting roles be assigned to teams such as platform admins, DevOps, or auditors. Service accounts work differently. They are Kubernetes native identities for pods, controllers, operators, and automation. For PAM, that means one governance path for people and another for workloads, tokens, and machine-to-machine privileges. RBAC in Kubernetes answers 3 questions. Who is making the request? What actions are they allowed to take? And where does that permission apply? The who may be a user, group, or service account. Permissions are defined in a role for one namespace, or in a cluster role for cluster-wide or reusable rules. Bindings connect those permissions to identities. A role binding applies inside a namespace. A cluster role binding applies across the whole cluster, so it should be treated as high risk. When a request reaches the API server, RBAC checks these relationships and returns allow or deny. One useful way to read an RBAC permission is as a sentence. Who can do which action, to which object, in which API, and across what scope? Verbs are the actions, such as get, list, create, delete, or impersonate. Resources are the targets, such as pods, secrets, roles, or nodes. API groups identify which Kubernetes API owns the resource. Scope determines whether the rule applies in one namespace or across the cluster. The key security lesson is that not all verbs carry the same risk. Reading pods is usually low risk. Creating pods, reading secrets, binding roles, or impersonating users can become privilege escalation. Human access to Kubernetes should be a controlled workflow, not a standing privilege. An administrator may start from an approved identity path, such as OIDC, Cloud IAM, certificates, or kubeconfig, but PAM becomes the policy gate. It verifies MFA, checks conditions, confirms approval, and grants only the role and time window needed. Prefer short-lived tokens or certificates over permanent admin credentials. Routine operators should receive limited RBAC permissions, while cluster admin access is reserved for emergencies. Finally, every API action should be logged and reviewed, so access remains accountable end-to-end. Service accounts are the identities workloads use when they talk to the Kubernetes API, so they need the same scrutiny as human users. The safe pattern is straightforward. Give each workload its own service account. Bind only the permissions it truly needs, and avoid relying on the default account. If a pod never needs API access, disable automatic token mounting entirely. The risk is escalation. A compromised pod with an overpowered token can read secrets, change RBAC, or affect nodes, turning one workload breach into a cluster compromise. Cluster admin is the Kubernetes equivalent of a master key. If a developer group is accidentally bound to it, every member can read secrets, change RBAC, create privileged pods, and alter cluster settings across every namespace. That is not convenience. It is a takeover path. An attacker only needs one compromised developer account to move from broad access to secret theft to persistence to disruption. Treat cluster admin as break glass access, not daily access. Require approval, limit duration, log actions, and review bindings regularly. The safest cluster is one where unrestricted power is rare, visible, and justified. A kubeconfig file is more than a convenience file. It can be a keycard to the Kubernetes control plane. It may include cluster addresses, user context, certificates, or bearer tokens. If that file lands in Git on a compromised laptop, inside CI variables, or in an exposed backup, an attacker may not need to exploit Kubernetes at all. They can simply authenticate. Treat kubeconfigs like secrets. Prefer short-lived credentials, require MFA-backed identity, harden developer machines, monitor unusual use, and revoke access quickly when exposure is suspected. Namespaces help organize workloads, but they should not be treated as hard security walls. The real risk appears when a compromised pod has permissions or configurations that reach beyond its intended scope. Privileged mode, host path mounts, host networking, or host PID access can expose the node. From there, an attacker may find service account tokens, secrets, logs, host files, or container artifacts. Even permission to create pods can become an escalation path if unsafe pod specs are allowed. The control point is admission. Enforce restricted pod security standards and block risky configurations before they run. Kubernetes secrets deserve the same treatment as production credentials because they often are. Start by limiting who can get, list, or watch them. Those verbs can expose every password or token in a namespace. Encrypt secrets at rest and harden etcd and API server access. Avoid passing secrets through environment variables when possible, and never let them leak into logs, images, or repositories. For stronger control, integrate Vault, Cloud Secret Managers, or CSI drivers, so applications can receive secrets without spreading static copies across the cluster. Privileged access in Kubernetes should operate as a lifecycle, not a permanent entitlement. A user requests access, an approver validates the need, the role is activated for a limited window, activity is monitored, and the grant expires automatically. For example, an engineer might receive namespace admin for 2 hours, while cluster admin remains reserved for audited break glass events. Tie access to enterprise identity through OIDC or Cloud IAM, then map groups to Kubernetes roles. Review RoleBindings, ClusterRoleBindings, service accounts, and unused permissions regularly, so least privilege stays accurate over time. Kubernetes PAM works best as layered control around the control plane. Preventive controls stop bad privilege used before it lands. Admission controllers validate requests. Policy engines enforce pod, network, and RBAC rules, and Cloud IAM ties cluster access to managed identities in AKS, EKS, or GKE. Detective controls make privileged activity visible. Audit logs should capture RBAC changes, secret reads, pod creation, and impersonation. Those signals then flow into SIM or SOAR, where teams alert, investigate, report, and trigger remediation. The goal is simple. No privileged action should be unauthenticated, unvalidated, unlogged, or unactionable. Kubernetes PAM is traditional privileged access management adapted for dynamic API-driven systems. The discipline is the same. Know every identity, scope every permission, protect secrets, and monitor continuously. Pay special attention to cluster admin misuse, broad service accounts, exposed kube configs, namespace escape, and secret leakage. Next, we'll focus on stronger secrets protection with Azure Key Vault and HashiCorp Vault.